are studying modeling of three-phase distribution transformers. It may be full three-phase transformer or three single-phase transformers are connected in different fashions. And what we did, we tried to derive the ABCD parameters of different connections of the three-phase distribution transformer. In that, basically, last two lectures we have seen 4 different connections, and we have derived ABCD parameters for those 4 different connections. To derive the ABCD parameter, we have seen that we need to get voltages in terms of line to neutral voltages and currents in terms of line currents. So, and those define your ABCD parameters, and for various combinations from last 2 lectures we have derived various ABCD parameters for different configurations. First configurations which we had considered was grounded Y by grounded Y connections. It is both side, it is Y connection, LV side as well as HV side, and both side the ground is there, and it is 0 connection, there is no phase shift between primary and secondary quantities. So, vector group is YG 0, and for that we have derived ABCD parameters, and basically we have got this is your A parameter, AB multiplied by ZT, AB is B parameter, and this is your D parameter. C parameter is actually 0 0 0 here. And for that, if your ZABC is basically matrix of ZTA, ZTB and ZTC, which are basically impedances in all 3 phases, and if you consider them equal, you can get simplified form of these equations, where NT you can take it common out, because AV is also matrix of your turns ratio, that is NT, 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 which are basically diagonal elements. So, NT can be taken it out. So, in that case your AV will become NT multiplied by unity matrix, and AV multiplied by ZT ABC will become LT multiplied by ZT. Here I am considering your ZTA is equal to ZTB is equal to ZTC. So, in that case your ZT will come out, which is basically equal to ZT, and then unity matrix will remain here. Exactly same thing we can apply for AI. AI is actually matrix of 1 by NT in diagonal elements. So, in that case also 1 by NT will come out, and it will be just unity matrix. Exactly similar way we have got ABCD parameters for delta grounded Y connection. So, in this case it is D, YG is grounded Y and 11. So, vector group is DYG 11, and for that configuration you have your A parameter, which is W multiplied by AV, where this W matrix is given by this one, which basically converts into your line to line voltages into line to neutral voltages, and then your B parameter will be W multiplied by AV multiplied by ZT ABC, and your D parameter will be K multiplied by AI. Again apply similar simplification by considering same tap position in all the 3 transformers. In that case NT will come out. Similarly, considering same leakage impedances in all the 3 transformer, your ZT also will come out, and in that case your simplified matrices A matrix will be NT multiplied by W, B matrix will be NT multiplied by ZT multiplied by your W matrix, and your D parameter will be K divided by NT. In the last lecture we have derived for 2 different transformers, those are actually ungrounded Y by delta connection. So, this particular vector group is Y, D and 1, and for that connection you have got A parameter, which is AV multiplied by D, where this D matrix is given by this one, which basically converts your line to neutral voltages to line voltages, and then your B parameter is AV multiplied by ZT ABC multiplied by L, and your D matrix is AI multiplied by L. In that case also applying simplification, that is all the transformer on same tap if they are single phase transformers, and self impedances, if they are same, they can taken it out. So, your A parameter will be simplified to just NT multiplied by D, and your B parameter will be just simplified to NT multiplied by ZT multiplied by your L matrix, and then your D parameter will be L divided by NT. And then lastly, we have seen delta delta configuration, and vector group is DD0, and in that case your A parameter will be W multiplied by AV multiplied by D, and your B parameter W multiplied by AV multiplied by ZTBC multiplied by M, and your D parameter will be just AI, which is just diagonal entries 1 by NT, 1 by NT and 1 by NT. So, in this case also, considering all the transformers, if they are single phase on same tap position, and your leakage impedance of all the 3 transformer, if it is same, then it can be taken common out, and then this is your simplified A parameter, this is your simplified B parameter and simplified D parameter. C parameter is always 0. So, in last 2 lectures we have seen 4 connections of the transformers. One is grounded Y by grounded Y connection, which is given by this expression YG 0 vector group. Then we have seen delta grounded Y connection, which is represented by DYG11, which represent plus 30 degree phase shift. And then we have seen ungrounded Y delta connection, which is having minus 30 degree phase shift, so it is YD1. And then we have seen finally delta delta connection, which is having phase shift of 0. And the ABCD parameters which we got for these transformer connections are summarized here. So, for grounded Y by grounded Y connection, these are your 4 parameters A, B, C, D. In case of delta grounded Y connection, we need one transformation from voltages which are basically delta voltages to the line voltages. In that case, we need that W matrix. So, that conversion is represented by this W matrix here. Similarly, we need current conversion also. So, delta currents in primary will be converted into line currents, and those conversions will be represented by matrix K. In Y delta connection, ungrounded Y delta connection, which is 3, we need on left hand on low voltage side one conversion, that is line to neutral voltages to line voltages, and that is done by your D matrix here. Similarly, we need current conversion, and that is represented by L matrix, where we need line currents need to be converted into delta phase currents. Similarly, here we need L matrix, and in case of delta delta transformer, we need 2 conversions, means first line to neutral voltages will be converted into line to line voltages, and then line to line voltages will be converted into again line to neutral voltages. So, here we will get both the matrices, that those are W and D, because conversion is happening twice. Current conversion is also required, that is why you are having this L matrix here, and here in case of D parameter, you will be having 1 divided by NT multiplied by U, because when we are transforming current 2 times, you are actually cancelling your L matrix with respect to your K matrix. So, in that case it will be 1 divided by NT multiplied by your U. Let us see one example. In this particular example, I am considering our general transformer, which is 3 phase 200 kVA. Voltage rating is on primary side is say 11 kV, secondary side say 433 volts, frequency 50 hertz, connection on HV side say delta, connection on LV side star with neutral bought out, which can be grounded, and say vector group is DYN11, which we already studied, depending upon the connections, vector group may change. So, in this case we are considering dyn. Also remember that all the matrices which are derived, that is D, W, A, V, all the matrices may be different for different vector groups. So, we need to, for particular vector group, we need to derive these matrices. So, in this particular vector group we are already derived, we can take them directly. Then percentage impedance is actually 4 and its angle is 87 degree. So, by knowing this data of any general transformer, we can derive the ABCD parameters for them, and you can use this ABCD parameter for any kinds of analysis. So, let us see how we can get ABCD for parameters for this general transformer, which is we may find in various our Indian distribution systems. So, we can easily find out turns ratio. So, for turns ratio we need to know, because on a primary side it is delta. So, across the winding there will be line to line voltage, and secondary side is star connected. So, across the one winding the voltage will be line to neutral voltage. So, in this case kV line to line voltage we know that it is 11 kV, and kV line to neutral voltage on LV side it is 433 is actually line to line voltage. So, we need to convert into line to neutral voltage. So, we have to divide it by √3, and the kVA rating given is say 200 kVA. So, we can get the turns ratio from this, which comes around 44.0 something. So, we can take that 44 here. Then I have drawn these connections. So, primary delta current connected, secondary is star connected, which is basically grounded, and then we need to calculate this ZTA, ZTB and ZTC. We can assume them equal because it is full 3-phase transformer I am considering. I am not considering 3 different transformers which are connected in delta star fashion. So, it is full 3-phase transformer. So, in that case we can assume that the leakage impedances are same, and those can be calculated using the percentage impedance which is given. So, percentage impedance is basically 4 angle 87 degree, and if you can convert into complex number form, it will be this number, that is 0.0021 plus 0.0399 I, it is complex number. Z base impedance, we know that it is kV line to line square divided by MVA rating of the transformer. So, from the kVA rating, MVA rating will be actually 0.2 MVA. So, by doing that you can get your base impedance, which is 0.9374 ohm, and then actual impedance of the transformer will be nothing but your per unit impedance multiplied by your Z base, which will give actual impedance, and we are assuming that in all the 3 phases this impedance is there, and this impedance which we have calculated on the secondary side. So, this is Z base which you have calculated on secondary side, because I am taking here kV line to line voltage, which is basically secondary side, that is 0.433 its square. So, it is on a secondary side. So, we have got actually impedances which are referred on secondary side, and then we need to get ZT-ABC. So, ZT-ABC is nothing but these 3 terms which are basically diagonal entries of ZT-ABC matrix. So, the same impedances I am putting at those, and as we have derived your A parameter for the vector group which you have considered, that is DYG11, which is basically DYN11 here. For that we have got A parameter which is NT multiplied by W, and we know the W matrix which is given by this, which you have derived, which basically converts your line to line voltages to line to neutral voltages, and NT multiplied by W. NT we have got which is 44, and W which you have got this matrix here. So, 44 multiplied by W matrix will give me 80 matrix. So, we have got A parameter matrix. Then B parameter matrix we have NT multiplied by ZT multiplied by W. So, basically this term we need to multiply it by your ZT matrix. So basically this is multiplication of this matrix multiplied by your this matrix. So if you can do this, you will get matrix which will basically this. So this is nothing but your B parameter here, and as I told you, C parameter will be 0 because we are not considering any shunt branch here. However, if you consider that magnetizing shunt branch, there will be some component in C matrix also. So since we have neglected your magnetizing branch, C matrix is always we are getting 0 for all configurations. And D parameter we have seen, this is K matrix divided by NT, and K matrix we have derived for this vector group which is given by this, and if this divided by 44 will give me this matrix which is basically DT matrix. So we have got all the parameters, that is A, B, C, D parameter, and those parameters we can use to get various other parameters. So till now we have seen the configurations which are 3-phase configurations. Now sometimes we need to use what is called as open Y open delta connections. It is basically valid if there are 3 single distribution transformers, or you can say if there is load which is having some load with single phase load and some load is 3-phase load. In that case, to supply that 3-phase load we need to have 3 single phase transformers. However, that 3-phase load can also be supplied by considering only 2 transformers, and that particular connection is called as open Y open delta connection. So let us see how we can use only 2 transformers to supply both the types of load, that is single phase load as well as 3-phase load. So in this case as I told you, we are going to use only 2 transformers. So let us say these are the 2 transformers here. And then I am taking the impedances on secondary side. So these are the impedances. Now connection on primary side is Y connected. So we need to take this 2 terminal out, and to make the common point for Y connection, and so 2 windings, 2 terminals will be shorted and then it will be grounded. So this is basically your ground connection here. This will be your A terminal, this will be your B terminal, and on secondary side we need to connect them as a delta. So we can connect them here, and third transformer is not there, so it will be open delta here, and this will be taken as your C terminal. The current which is flowing through this is I am calling IC. This will be taken as your small a terminal, current is IA, and this terminal is taken as your B terminal, and this current is I am calling it as small IB. This current will be current IBA, and this current will be current ICB, and ICB and IC they will be opposite in direction. In this case this will be your current I capital A, and this will be I capital B. This impedance ZTAB because we did between terminals A and B, and it is ZTBC because it is terminal between B and C. This voltage across winding, it is VTAB, this is VTBC. In this case, if you observe this voltage across this, it will be V capital AG, and this will be capital VBG. Now if you can see how it is converting your 2 single phase voltages into required 3-phase voltages. So in this case, if you see, suppose your vector VAG, it is basically in this direction, then your VBG voltage will be 120 degree shifted with respect to this, and this will be your VAG and VBG. Then we know that voltage VTAB will be just in phase with VAB if you consider dots here. So VTAB will be in phase with VAG. So your VTAB will come somewhere here in phase with VAG, and VTBC will be in phase with VBG. So, this will be your VTBC. Your VTAB plus VTBC plus VTCA, they will be equal to 0. So, in that case VTCA will be equal to minus VTAB minus VTBC. So, your minus VTAB will come somewhere here. So, this will be minus VTAB and minus VT will come somewhere here. So, this will be your minus VTBC, and if you add these two vectors, you will get third vector, because VTCA is addition of these two minus quantities. So, VTCA will come somewhere here, and if you calculate the angle between them, they will be 120 degree shifted. This I am considering during no load condition. This condition will be valid during no load condition. So, during no load condition, at the terminal we are getting completely 3 voltages which are basically 120 degree phase shifted. So, required 3 phase voltages we are getting from only 2 transformer. That is why sometimes instead of using 3 transformer, we can save 1 transformer cost by putting only 2 transformer which can supply both the types of load. Those are single phase loads as well as 3 phase loads. So, that is why your open Y and open delta connection sometimes become important. Let us see how can we derive the ABCD parameters for this particular matrix here, this particular transformer here. So, in this case again I am taking that transformer on primary side which is basically Y connected, open Y, because third transformer is not there. In this case secondary is delta connected, open delta, because third transformer is not there, which basically makes you delta closed. Now, if you write the equation for this voltage, which is basically VTAB, will be nothing but voltage VAB, which is basically between A and B terminal, VBC is between V and B terminal, and VCA is between C terminal. So, this is basically small a terminal, small b and small c. So, VTAB will be nothing but this voltage plus voltage drop which is happening across this. So, basically it will be given by this equation where the current is IA. In this case this voltage drop VTBC will be nothing but, so VTBC will be nothing but VBC plus JTBC multiplied by ICB. However, ICB is nothing but minus of IC, because direction of ICB is like this minus direction of IC is like this. So, in that case it will be VTBC will be equal to VBC minus JTBC into IC. So, basically you will get this equation here. Now, we can put these two equations into matrix forms. Before putting matrix form, let us derive the this turns ratio condition also. As I told you, this VAG voltage and VTAB and VBG and VTBC, they are just related by turns ratio. So, VAG will be nothing but VAG will be equal to your NT multiplied by VTAB, and VBG will be equal to NT multiplied by VTBC. And if you put these two equation into matrix form, basically I will get this equation. There is no VCG voltage because third transformer is not there. So, we can put 0 0 0 as a column as well as row, and VTC is also not there. So, that is why just we have augmented this matrix by putting 0 0 0. So, in that case your AV matrix will be basically this just modified AV matrix, and this will be nothing but your VLG ABC, because they are line to ground voltages, and on this side this is VT ABC. And now these two equations, what I can do, I can just multiply this equation everywhere by NT, both side NT, and this we know that NT multiplied by this will be V AG and this is V BG. So basically these two equations, after multiplying NT, I am getting two equations here, which then I can put into matrix form. So these two equations 1 and 2, which I have taken from last slide, and if you put them into matrix form, so first equation if you put into matrix form, it is basically this equation, and second equation which is basically this equation, and in this case there is no term which is related to CG, so that is why this row I am making 0, but however there is entry related IC, so this term will get multiplied by IC. So if you put these two equation into matrix form, I will get this equation here, and in condensed form I can write these equations. So these are nothing but line to ground voltages of all the three phases. This I am calling matrix AV. These are basically line to line voltages on secondary side, that is why VLL small ABC, and this is nothing but your B matrix, and this is IABC. Only here this is okay because VLG ABC we are getting a required format, that is line to neutral. However, these are voltages line to line voltages which need to be converted into line to neutral voltages. So this can be converted by writing this term as a writing D multiplied by VLN, because here we need to convert line we need to get line to line voltages from the line to neutral voltages. In that case your conversion matrix is D here. So thus your AT matrix will be AV multiplied by D, and in that case AV is little bit modified as compared to earlier AV matrix. D matrix is same which you have seen earlier, and your B matrix will be basically this matrix for open delta, open Y open delta configuration. Now let us try to derive for C and D. So as we have seen, to get C and D parameter we need to get the relation between currents. So in this case if you this current IA and current IBA, they are just related by your turns ratio. So your IA will be equal to IBA divided by your NT, and your IB will be equal to ICB divided by NT. However, this IBA is same current which is coming and going here. So IBA and IA, they are having same direction as well as same magnitude. So IBA can replace by IA, so it will be IA divided by NT, and ICB is having opposite direction as compared to your IC. IC is in this direction, ICB is in this direction. So I can say it will be minus IC divided by NT. So I can write this into matrix form. So which you have got actually IA will be equal to IA divided by NT, and we have got IB will be equal to minus IC divided by NT. So these two equations which I got on last slide I put into matrix form, and in this case this will become your D matrix and C matrix will be 0 0 0, because again in this case we are not having any shunt branch. So in that case your C matrix will be 0 and D matrix will be this one. So we have got C matrix and D matrix also. Let us see how we can get capital A and capital B matrix. So as I told you, for getting capital AT and capital BT matrix, we need to write equations of V secondary voltages in terms of primary voltages and secondary currents. So basically this equation we need to convert into secondary voltages. Basically these voltages I need to write in terms of primary voltage and IA. So we can just rewrite them. by taking VAB on this side and VAG on this side. So basically if you rewrite them, it will be VAB will be equal to VAG divided by NT and minus this term, that is ZTAB dot IA. Again if you write this equation, I will get this equation here. So it will be we can write them into matrix format. So in this case also on this side all the 3 voltages I have written. However, we are not having equation for this VCA equation. So and on this side we are having VAG, VBG and VCG, and there is no term into this equation related to VCG. That's why all the 3 entries which are getting multiplied to VCG they are 0, and then VAB is equal to VAG divided by NT, which term here, and then ZTA minus ZTAB into IA, and from second equation we are getting this term here, and third equation we are getting from adding all the 3 voltages on the secondary side. So basically we are getting this by adding all the 3 equations. So basically we know that VAB plus VBC plus VCA should be equal to 0, and in that case your VCA will be equal to minus VAB minus VBC. So VAB is this one, VBC is this one, I can put into this equation, and from that I will get this third equation which I am putting it here. So it will be basically if I add these 2 quantities, it will be minus 1 divided by NT into VAG plus ZTAB into IA minus 1 divided by NT into VBG minus ZTBC into IC. So basically this third equation which I am writing it here is basically coming from this term. So these 2, 1, 2 and this third equation, if I put into matrix form, I will get this one. Now if you observe this equation, here we are getting line to line voltages. So I can write this is VLL ABC, this is okay. So here we are getting VLN or VLG capital ABC. So this is okay, and here we are getting line to current, so small ABC. Okay, so here we need to convert this line to line into line to neutral voltages. So basically here, so this will be actually VLL ABC. This I am calling BV matrix because it is little bit different than our earlier AI matrix, AV matrix, and here this is VLG capital ABC because line to ground voltages, and these are line currents. So here we need to convert this line to line voltages into line to neutral voltages. So we know that the multiplication matrix, which will be basically W. So every term into this equation need to be multiplied by W to get line to neutral voltages on left hand side. So this W multiplied by VLL will become line to neutral voltages on secondary side, basically this side. This W multiplied by BV will become your capital AT matrix, and W multiplied by your JT ABC will become capital BT matrix. And BV matrix basically we have seen on the earlier slide. So this is your actually BV matrix which need to be used here. Now see, many times in basically short circuit calculation we need to know Thevenin's equivalent circuit at that particular short circuit point. Say in this case what I have shown is there is source here, then this bus voltage is VLN ABC, ELN ABC I am calling, and then say there is a transmission line which is having impedance matrix of say Z system ABC 3 by 3 matrix of your transmission line. Primary transformer voltage VLN ABC, and secondary side it is VLN small ABC, and secondary current side current is IABC. Let us say fault has occurred at this point and we need to get the Thevenin's equivalent circuit till this point. We want to convert this whole circuit into just Thevenin's equivalent source and Thevenin's equivalent impedance. So, let us see how we can get this impedance here. So, if you see the voltages VL and ABC, these voltages will be nothing but these voltages here minus your impedance drop which is happening across this transmission line. So, that can be written by this equation. So, these voltages will be equal to these voltages here minus voltage drop which is happening across this line. So, this is nothing but your voltage drop across this. Okay. So, VLN ABC we got voltages at this point. We also know that the currents on a primary side of the transformer and currents on a secondary side transformer, they are related by just DT matrix, because CT matrix they are it is always 0. So, IABC currents on a primary side will be nothing but your DT matrix multiplied by current on secondary side. So, we already seen many times this one. So, what we can do actually this I can put into this expression. So, here it will get multiplied by dt multiplied by IABC. Instead of I capital ABC, it will be dt multiplied by I small ABC. Then the voltage relations, we know that secondary side voltages of the transformer, that is VLN ABC, can be written into primary voltages and your secondary current, and we have seen that for that particular case we need to use capital AT and capital BT matrices. So, this voltage VLN ABC will be equal to AT matrix multiplied by this voltage minus BT multiplied by your line currents. So, basically we can get this equation here, and in this equation whatever VLN which you obtained earlier I can put it here. So, instead of VLN AB capital ABC I can put this term here which is basically this term here, and then you just simplify it so that the terms related to current IABC I can take it together. So, I can just expand it by multiplying this AT matrix inside this bracket here, and from that this is term which is related to IABC and this is IABC, I can combine it together. So, basically I am getting this term here. So, IABC is taken common out of from these two terms. So, in bracket we get this term, that is, and remaining term is this one. So, by seeing this expression here, say expression 1, we can easily get Thevenin's equivalent circuit. So, basically if you observe this, this equation will be nothing but something like this, where it will be ETH. So, this is nothing but your ETH minus this will nothing but your ZTH into IABC. So, basically this will be nothing but your ZTH, which is this bracketed term, and ETH which is Thevenin's equivalent voltage source, which is given by AT multiplied by ELN ABC. So, as I told you, this will become your Thevenin's equivalent voltage source and this will become your Thevenin's equivalent impedance. So, in the summary, we have finished your transformer modeling part, and in this particular lecture we have seen that summary of 3-phase transformers, how they are modeled. So, we have summarized all the 4 connections or 4 configurations which you have considered. We have summarized them in one of the table. Then we have seen one example where normally used transformer from Indian distribution system, I have taken it here, and we have derived ABCD parameter for those transformer. And then we have seen finally we have seen what is called as open Y and open delta connections, and I have told you the applications of this particular connection where we save one single phase transformer, and we have derived again ABCD parameter for these configurations. And finally we have seen that how we can get Thevenin's equivalent circuit if there are transformers into your circuit, and if you want to get your Thevenin's equivalent circuit till your point of interest or where you want to calculate the short circuit current, you can get Thevenin's equivalent circuit. So in this particular case I have considered only one transformer. So even if there are many transformer into your network as well as many transmission line, we can easily find Thevenin's equivalent circuit by using the methodology which is explained in this particular lecture. So here we finish our transformer modeling part, and next time we will see how we can model the voltage regulators. Thank you.